bit. So we started looking into lambda levels of the sphere. So let me shortly remind you of the main two formulas that we need, because some people in the audience haven't been here yesterday.
Even cost.
So we're talking about a Hamiltonian. Oh, that doesn't work. We're talking about a Hamiltonian which just contains the canonical angular momentum operator. The operator was defined to be r plus minus I gradient plus dA of r. So then we started talking about details of how we were implementing the spherical coordinates in order to solve this problem. And then we also realized that this angular momentum lambda, the way we've written it down, actually is not the generator of rotations. This is just the kinematical part of the angular momentum that goes into this rotor Hamiltonian. What the full canonical angular momentum actually is, and you were supposed to review that from the computation relations that I helped you obtaining, is that you find a new angular momentum operator, which then does the job of generating rotations around the origin of the sphere, which is visible by the commutator with any vector operator. Okay, so then the next thing that we did is we noticed that ER projected on capital lambda is 0, as a consequence of this, lambda squared is just L squared minus S naught squared, just by squaring that equation. And from there, it was then easy to obtain the spectrum of lambda squared, for the reason that for L, because this is truly just related to the generator of rotations, we could quantize it according to S times S plus 1, and we could also find the second condition, that this S that enters the eigenvalue of the squared angular momentum operator was S naught plus n, where S naught, if you recall, was parametrizing the number of Dirac flux quanta in the center of the sphere. That is so important that I don't mind writing it down again. So if we have a magnetic monopole in the center of the sphere, then the ratio between the magnetic flux divided by the Dirac flux quanta was 2S naught, which has to be element of the natural numbers due to Dirac quantization. Okay, so as we start this in here, I could find the energy eigenvalues as a function of this parameter small m, and that turned out to be omega c over 2s naught, s times s plus 1 minus s naught squared, which is omega c of n plus 1/2 plus some correction, and this correction vanishes as we allow the number of states on that sphere to be bigger and bigger, which is to say as we increase the number of Dirac flux quanta, which is to say we increase S naught. So in that limit of an infinite sphere, you recover the expression that we had for the planar geometry. Okay. So now that this is how far we got last time, and now we want to address the question of understanding more about the eigenstates themselves. And in order to do that, we have to pick a gauge for A, because the only constraint that we have was that the rotation of A was the magnetic field pointing in radial direction. That's the thing that we can request from the situation that we have a magnetic monopole in the center of the sphere. Okay, so let's pick a gauge and let's think a little bit about the gauge that is chosen. The gauge that I want to pick makes the vector potential look as follows. So why do we pick this? As we now compute the rotation of A, and you can use the small formulas that I gave you last time, as we compute the rotation of A, we obtain S naught over E 1 over R squared dr, and that was supposed to be the magnetic field direction. Now, we are having, what we're facing here is a magnetic monopole, and then who of you is familiar with the gauge problem of magnetic monopoles? So let's look into this. So there's this issue of the following kind, because I think I have too much material to cover, then we'll be a little bit short on that. The general argument goes like this. Of course, we want to have the magnetic field defined by the rotation of A, but at the same time, we can also have a look at the divergence of B. Okay? Let's have a look at the divergence of B. This is something like the divergence on R over R cubed. This is something like the Laplacian of 1 over R, and this is the delta distribution function of R, and that is unequal to 0. Whereas we would actually request that since the magnetic field follows from the rotation of the vector field, there's no way that we can consistently fulfill a divergence of B that is non-zero and a rotation of A that is B.
Why do we need that? Don't we only need it on the surface of the sphere?
Sorry, could you say that again?
So our whole theory is defined on the surface of the sphere.
Yeah.
What does it matter what happens away from that surface?
Oh, no, it matters in the sense that we have to ask ourselves, how do we describe the magnetic monopole? And I'll show you in a second how that is treated in this choice of the gauge. I'll come to your question in one minute. So instead, what we're doing here is we have to impose Dirac strings. And how people usually talk about it, if I have a magnetic monopole, can I look at this monopole from whatever distance? Let's fix the distance r. I need to have a point on the surface of r where the Dirac string penetrates the surface and connects to the magnetic monopole. And this Dirac string has to be chosen in such a way that this divergence of B actually becomes consistent with being generated just from the rotation of a vector field. So we just add manipulations to the vector field A in such a way that both expressions hold. And this is with which I want to leave you on the general problem of Dirac strings. There's even also a way to formulate monopoles without Dirac strings. So the question of how to make a magnetic monopole become gauge invariant has been an ongoing, interesting, and actually fairly accessible matter of physics, also in high energy. I rather want to spend 2 minutes on how it is solved in this case, because that deserves mention. Usually, when you want to say we have one Dirac flux quantum in here, we want to think of the Dirac string as a flux solenoid, you say? As a flux solenoid by which we thread the flux into the center of that monopole. And the flux 2 pi, well, in appropriate units, of course, the flux 2 pi is usually threaded by one solenoid. And then people will start to argue, as a function of gauge transformation, the position of the solenoid changes. And if you were to do an interference experiment, you wouldn't be able to detect that solenoid. which is why it can't be of physical significance, and it's just a feature of the accurate theoretical description. What is a study that is probably too much effort for you to do now is to appreciate that this is not exactly the path taken here. What this thing does is, it doesn't take a single Dirac string of phase 2 pi, it takes the quantum Hall sphere, defines the north pole and the south pole, here's the magnetic monopole, and it threads half of the Dirac flux from the north pole and half of the Dirac flux from the south pole. So what is really happening in this pit, this kind of gauge, you can think of the total flux is 2 times S naught times Dirac flux. So there is phi d S naught coming from the north pole into the sphere, and there's phi d S naught coming from the south pole of the sphere. Okay? And let me show you why this is so. For that purpose, I'm sorry that the presentation gets a little bit, maybe I take another, I go to the next board already, but this is the picture that you should have in mind. This is how the solenoids are accounted for. And I show you how you can improve that, or how you convince yourself from it. Let's just have a look at the North Pole. And let's do a small circle around the North Pole on our sphere. Okay? And let's just calculate the flux through that little radius. Okay? So if we do that, the flux is dA, which is just the line integral of A along R. By R, let me define the radius of this small thing. This is R, this is small r. So you get what I'm saying. This is the North Pole. So as we do the calculation here, let's plug in the values here. So this is minus r d phi, where phi is just the angle along this trajectory, minus r d phi, s naught. I'm just plugging in the values. Er and the cotangent I just write out as cosine theta over sine theta. Now, when I take an arbitrarily small region around the North Pole, I can expand in theta, because theta started to be 0 here, so sine theta is something like theta, and cosine theta is something like 1. So I reduce this to be 1 over theta. Theta times r is small r. Small r and this small r cancel each other. Can you follow, or should I break the intermediate step? I think you can follow, right? Yeah. So this then becomes as not, where am I? Yeah. This is minus 2 pi over E as naught. And you recall we put the units h and c to equal to 1. You can just, this is in the appropriate units, minus phi d as naught, which is what you wanted to show. And the same thing applies to the South Pole. So what is kind of cool about this implementation, this is in Paul Dane's paper, and he doesn't mention a single word of it, he uses a split Dirac string. He uses 2 Dirac strings where the magnetic flux is pumped into the magnetic monopole from the north and the south pole by an equal amount. And why he does that gauge fixing is that assures inversion symmetry on the sphere. So if I had just, even in this gauge, the inversion symmetry on the sphere is kept. That's why he does that without ever mentioning it. Okay, that's important. Okay, so with this, now let me come to the central problem of analysis that we would have to solve alone if we didn't have Dr. Thomale on our side. Namely, the main problem is, let's look at this lambda squared in that gauge, and this lambda's, gamma's. No, this is capital minor. Yeah, lambda squared. let's look at lambda squared, and the differential operator that you obtain, you can easily obtain it with the formulas that I gave you with these derivatives. You have to put this in. It looks like 1 over sine theta partial theta of sine theta partial theta minus 1 over. When it's just inserting values, I don't say check. You should check anyway. I mean, this is not a big exercise, but that's simple, and you obtain this expression. And basically, what we're supposed to solve now is this differential operator. And it doesn't look that simple. And the next stroke of ingenious choice done in this paper by Ronny is to think about how we should reconcile this operator. So far we've been using the spherical coordinates, and since we're living on a sphere, we only have the theta and the phi. But the problem is a little bit that this coordinate system rotates with you on the sphere, depending where you are. And you can't really localize a particle, for example. So if I have an eigenstate of the angular momentum, it is by definition delocalized. But what I would really like to have is, I would like to have an actual variable description that allows me to specify a point on the sphere, and not just an angular momentum orbit. Those parts of the problem are not relevant for us because Duncan Cornell in the end needed this to set up an appropriate single particle basis for the many-body problem of vector-form Hall effect he wanted to study here. But still, for us, it's extremely convenient to adopt the notation. And this is what he calls spinor coordinates. And the spinor coordinates are defined like this. I define a coordinate u equal cosine. It's just a new set of coordinates. I had two coordinates, theta and phi. Now I get two other coordinates, u and v later on, but I'll show you. Cosine theta over 2, e to the I phi over 2. And v is sine theta over 2, e to the minus I phi over 2. And I define the complex conjugate, just that you know how, so in the paper, it's bar, but what it really is, it's just the complex conjugation. And those are the coordinates. So let's have a look at them. Oh, I'm sorry, I just noticed that my u and my v are very similar. So this is a u, this is a v. Okay, we don't have enough time to really discuss that, but I want to stress, I just make a check here. Think deeply about these spinor coordinates. Because they are extremely important to appreciate. So let me guide you towards certain aspects of them. Look at what happens when I turn phi to 2, if I shift phi by 2 pi. I actually pile up a minus sign here, okay? So when I form wave functions, out of these spinor coordinates, they're actually double valued. And this double valuedness is, let's come back to this later, but notice that choosing the spinor coordinates is far from trivial, far from clear, and I have to prove to you that this is actually any useful. Okay? But let me just use this set of coordinates, and let's move on with this. So the radial vector of spherical coordinates, that's the first main thing that you should appreciate. Can be, and I just use the notation that you would find in Duncan's paper, can be associated with an orientation vector that depends on the spinor coordinates u and v, and you can rewrite it as u and v transpose Pauli matrix vector u bar v bar, and the sigma is the Pauli matrix vector. So what this is really saying is that I can, by specifying a pair of spinor coordinates, I can fix the the point that I'm looking at. Okay, so that gives you the right feel for those spinor coordinates. Here, the E of R, if you say, okay, give me the E of R, you would always have to ask, ER is not specified. It could point in any direction on the sphere. But I can give you a very specific set U and V of coordinates, and this U and V of coordinates is specifying a particular direction that then reconciled in spherical coordinates according to U and V corresponds to the radial vector contribution.
So Ronny, I know you said very much how does the difference in theta and phi?
Sorry?
Okay.
Yeah, I come to that.
Theta and phi also specify a location very well.
Yes, exactly. And the subtlety will come as soon as we try to rewrite the eigenfunctions of the problem either in spinor coordinates or in spherical coordinates.
So I think all what you're saying is we can use U and V as just as well as we use theta.
Yeah, not fully. But I haven't yet shown you the coherent states that we can write down in terms of the spinor coordinates. And you should appreciate that this double valuedness is at the heart of solving the problem actually. So there are subtleties involved. But let's just go on to the calculation. And so instead of
Ronny,
yes,
this is all because S0 is not 0.
this is
okay.
okay.
0, 0.
No, if you really want to have
the y labs.
the answer would actually generate more questions probably that I'm going to give. But if you want to have a truly slick response to that, you want this because S naught can be half integer. S naught can, 2S naught is integer, but S naught can be half integer. And in those cases, it's just wonderful to have the double value spinor coordinates under the transformation ring. Phi goes to 2 pi because what it really does is it picks up a pi phase. Right, it's to move around the sphere.
But isn't it true that S0 is 0, the eigenfunction?
No, but S0.
Y left.
Yeah, but if S0 is 0, then basically we don't have any magnetic monopole. So then that is trivializing the problem, and nothing is left. So S naught, S0 is finite.
Some generalization of your spherical harmonics on 0, S0.
Oh, so when we're living on the sphere, and the spherical harmonics are just a complete basis, whatever we do on that damn sphere will be some variation of spherical harmonics. The question is just, what is the most accurate basis to solve the problem? And then just quickly guide you through it. I have time till 2, right? Yeah. So, let me get for you the complete orthogonal basis of the lowest lambda level on that sphere. Complete basis of the lowest lambda level. Psi n naught is equal to S. Let's forget about normalizations for the moment. We can get them later. Minus m, and m is element of minus s up to s. So n in total takes 2s plus 1 different values. This is the wave function that I want to write down in terms of scalar coordinates. And let's see whether this thing solves the problem. LZ applied to this psi m naught. So let's just get the notation right, because I also introduced to you the planar problem of lambda levels. There we had the guiding center quantum number that was m. The n is the lambda level. Since I'm in the lowest lambda level, there's a 0 here. And S is describing the value. Well, I could also write S naught here, because basically we're in the lowest lambda level. So S is S naught plus n. So I could also write S naught here, but I leave it as a general thing. S naught is describing the number of Dirac quanta in the problem. And this is characterizing what wave function I mean. And this in total has this thing. The total power that you can already read off from here is, the total power is 2s. If I just for the moment forget about u and v, being different, the total power of the polynomial is 2s. And let's have a look whether this wave function would actually be a good thing in order to solve this awful differential operator. And LZ of psi and naught is just, well, LZ is very simple. This is just the generator of rotations around phi, so I can, without any thinking, I can easily see that psi m naught s has the eigenvalue m, right? Because I get, because the phi dependence only comes from the exponential here. So as a consequence, I would instantly get half of m half from the u coordinates and the other half from the v coordinates. So in total it's m. And then, and this is what I will prove to you now, h, this psi m naught is indeed an eigenstate of the problem. And which eigenvalue should it have when it's an eigenvalue to the lowest number level? What should be the energy? 1/2 cyclotron frequency.
Yeah.
Should you have the plus?
No, but n is 0.
One over s naught?
No.
No, but n is equal to 0. N is equal to 0. Okay, so let me show this to you. So to be proven as that this holds, and I actually would like to prove this to you because this proof is not in Duncan's paper. If you recalculate the paper, it's really important that you have that. So in order to prove that, and for the next, in 20 minutes, I need that equation again. This is why I'm writing it on here. Imagine I have a slightly more general polynomial that I parameterize by the quantum numbers m, p, s, u, v, and now I'm plugging in the values, cosine theta over 2, s plus m, sine theta over 2, s minus m, e to the I, n minus p phi. And that in the spinor coordinates is just v bar to the minus v, us plus m, vs minus m plus p for p smaller than 0, and it's v bar p us plus m minus p vs minus m, p larger than 0. So we can just apply lambda squared in this state, which is very simple. So it's really with the information that I gave you before, it is really not so complicated to check that this holds. Is equal to s minus s cosine theta minus m divided by sine theta squared plus s naught cosine theta minus m plus p divided by sine theta squared. Psi m ds, and if you work this out, you get s plus 2 s cosine theta minus m plus p, p minus n cosine theta minus p squared minus n squared cosine squared theta. divided by sine squared theta s. And now, if we want to connect this generalized state with this state, we can choose p equal to n equal to 0. And in such a case, we get that lambda squared sine of s is equal to s. And this is exactly the expression of it. Okay, and now that we convince ourselves that those are good eigenstates, also the normalization is not a big problem. The only normalization integral that you need is the solid angle integral over the spinor coordinates, and that is not so hard to do. It's just one Bornstein or Abramowitz integral. It's not complicated. Yeah, so this is basically solving our problem for the lowest lambda level. So we know the eigenstates. The eigenstates, so you have to, then I will put this down, because this is just the proof for something that is already here on the board. So look how beautiful you can write down these eigenstates in terms of spinor coordinates. Very simple, very elegant. This awful differential operator is solved by this type of eigenstates in spinor coordinates, and you can see from the Hamiltonian eigenvalue that they describe the lowest lambda level coefficients. Now, yeah, there's another subtlety. Maybe I will. Okay, so I will erase this board. So this is where basically the single particle study of eigenstates on the Haldane sphere ends in Haldane's paper in 1983. And you would ask yourselves, okay, so I mean, we can use this L operator, this canonical angular momentum operator, to label the different states in the lowest lambda level. And how many states were there? 2s plus 1, where s was where 2 times s was the total flux of the monopole in the center of the sphere. But then, when we discussed the lambda levels on the plane, we had 2 ladder operators. We had the ladder operators that allowed us to label the individual states in one lambda level with the same kinetic energy, and then the cyclotron ladder operators that allowed us to transform one state from one lambda level to the other. And this piece of information has only been accomplished in 2011, and let me shortly summarize that for you. So this L operator can be written. So that is this generator of rotations. And because it's a generator of rotations, it can be so nicely represented by Pauli matrices, right? So this was in our analogy. Those were the B dagger B operators on the planar investigation. Now the question is, what is the analog to A dagger A? Okay, and the solution to that is that on the Haldane sphere, basically you have 2 independent sets of SU2 generators. One SU2 generator rotates within the basis of one lambda level. It's also a representation of SU2. But then you have another algebra. Then you have another algebra of SU2 that governs the rotation between the lambda levels. And it's just a high symmetry avenue of the Haldane sphere that you have, in both cases, you just have SU2 generators for that rotation, either within the lambda level or out of the lambda levels. Okay? And well, let me try to make this short. The most efficient way to describe this new algebra can actually best be written by the spinor coordinates. So let me show you where is it. I have to shorten because I want to get to Dirac fermions. So this new what is the analog to A dagger A? Result, we find two independent algebras, SU2 algebras, that govern rotations in and out of the lambda levels. So unfortunately, due to lack of time, I can't be self-contained at this stage. I underestimated how much time I need for the previous stuff. So I give you the result of how the new operator looks. This L I just defined for you, it's within the lambda level. Now let me give you the other operator. This operator rewritten in spinor coordinates looks as follows. See something very interesting, I would say. Sorry?
No.
U bar, V bar, graph. E by U bar, V by
Yeah. Thanks. So this is the functional form of this operator. And what does it really do? Let me give you the result right away, which you can quickly get. The result is that the Hamiltonian on the Haldane sphere can actually be written like omega c over 2s naught times s minus s plus 1/2. Now that's interesting, right? So before, what was the Hamiltonian? It was just lambda squared. Now I can write down this Hamiltonian of the Haldane sphere just as ladder operators of the second algebra that was the cyclotron algebra. And this is what we would expect. I mean, imagine we had A dagger A to be the planar Hamiltonian for the lambda. So of course, on the sphere, in terms of an algebra that generates rotation between the lambda levels, that's how it has to look, right? And these, basically, it's in the sense self-contained that you have everything on the board that you need. How you obtain this algebra, you don't even need to know. I give you some little hints on how to check that it's the right one. That's all you need to check. And for example, convince yourself that ERL is SZ. Do this little exercise. Another exercise that you should check. You don't need much more. Do you realize that? Because then in the we had shown that, yeah. So then you need to convince yourself that L squared is equal to S squared. That's the other thing you need. And then what you can really do is, this is basically all you need. Once you have these two things, let me show you how the calculation goes. You start off from the original expression we had in the Hamiltonian, L squared minus ERL squared. This is what it was, if you recall. The projection of L on the radial direction was S naught. There was S naught standing here. Now that I have ER times L, now that I know that this is SZ, okay, I can just put in SZ squared here. And now that I know that L squared is equal to S squared, I can put in S squared here. Okay? And now S squared minus SZ squared, it's just exactly this final result. You can easily show. Okay? And this, I think, is quite remarkable, actually, casting, that you can actually work it out like that. Okay. And I don't have enough time to go through further details there. So basically, maybe one little point, the projection on L was as naught. So in a way, you see the radial projection of the angular momentum operator L is already telling you which lambda level you are in. Okay? This is sort of what it does. And now you see explicitly what I told you before on the plane. If I take an eigenstate from the lowest lambda level and I want to generate an eigenstate from higher lambda levels, what I have here is an annihilation operator as plus and a creation operator as minus. But by acting with a creation operator as minus, the S eigenvalue here gets reduced by 1. Recall how I talked about it on the plane. In this case here, the total number of states is 2S plus 1. If S gets reduced by 1, then the total number of states by which two finite size lambda levels differ on the sphere is 2 and not 1. So this is the last thing that we mentioned in yesterday's class. Okay? And so now with the 15 minutes left, I will actually even skip the Dirac lambda levels on the plane and rather go straight to the upshot of the whole lecture, which I have to cut down now, unfortunately. And for that, let me erase one last time this board and show you. So let's completely forget what we have done so far. What I discussed with you was lambda levels on the plane and lambda levels on the sphere. We encountered an awful differential operator that we managed to solve by spin-off coordinates. That's the only thing you need to know in order to listen to the next 15 minutes. When we talk about, I skipped 2.1, from my original plan, and I go to 2.2 immediately, the 3dTi surface. Okay? So we're approaching sentence problem. Who of you knows about the theta term in a topological insulator? Okay. So, a 3D topological insulator can be thought of separating two electromagnetic vacua that distinguish themselves by the presence or absence of an E dot V term in a time reversal invariant fashion. If I have, so what it gives rise to in the end of the day is a topological insulator is just an insulating state of matter that lives in 3D. So let's imagine a bowl of topological insulator. At the surface, this topological insulator has an unconventional edge theory. This is what Sento talked about. And in the case of a 3D topological insulator, you have a single Dirac cone on the surface. A single Dirac cone, let me stress that. So there's a single Dirac cone on the surface. Okay? Well, we can talk on and on now about the non-triviality of this statement, because in principle you would naively be led to say that a single Dirac cone is not gauge invariant. This is an even stronger statement than Fermat doubling. It has nothing to do with Fermat doubling at the end of the day. It's just saying that if I have a single Dirac cone and I gauge the Dirac cone, I will run into what high energy people would call parity anomaly. For the lecture, let's forget it, and let's just assume that this is right what I'm saying, that there is a state of matter that is an insulator in the center of the sphere, and we have a single Dirac cone at the surface. So let's adopt it. Yes, that's what I said at the beginning, assuming time reversal symmetry. So imagine that we have a single Dirac cone here, and we wanted to get a low energy Hamiltonian for the problem. Then what would we need? It's a single Dirac cone Hamiltonian on the sphere. And this is what Sento wanted to start with. This Hamiltonian is just written like this. This is what it is. For simplicity, that you really appreciate the terms, this is just a canonical momentum. But then cross sigma is just saying the following. Imagine I rotate it along the z-axis. Along the z-axis, I would have sigma x, and I would have sigma y. And if you recall the low energy description of the of graphene, for example, around k or k prime in the Brillouin zone, this is exactly what you get. On the off diagonals, you would have kx plus iky, and on the other hand, you have the Hermitian conjugate kx minus iky. So you can easily convince yourself that this is the right way of describing the Dirac Hamiltonian on the sphere. And people around Imura, that was the paper that I gave you at the beginning, Imura et al. Concluded that Hamiltonian really starting from the 3D topological insulator. So they did the hard job of calculating the 3D topological insulator and extracting the surface theory for that. That's a very sort of technically involved paper. And what they obtained was that they can write down this Hamiltonian in the case of a topological insulator in which we can just safely neglect the coupling to the E1 gauge field. We can basically say there is no magnetic field, there's time reversal symmetry. So in this case, this is why I'm writing down an H0. H0 3dTi by Imura was shown to take on the following form on that sphere. Phi, and the operator that they have, capital gamma, is minus I e phi partial theta minus e theta 1 over sine theta partial phi minus I over 2 sigma z. And that's not the Pauli matrix now, it's just saying if I have upspins, I want to be plus 1. If I have downspins, I want to be minus 1. So it's not a matrix. How should I? It's clear to you. So this is just saying plus or minus 1. Cosine theta. Now, okay, maybe it would be too quick to ask you to really see what is happening, but maybe you appreciate a little bit. So this lambda has some term in it that sort of depends on sigma z. So it's sensitive as to whether this operator acts on upspins or downspins. And this little term in this lambda operator we can actually understand better by looking. Okay, so this term we can interpret as a very phase contribution. But before we do that, let us just try to solve that together, and let us think how to obtain it. If we're now facing such a Hamiltonian, let me rewrite it a little bit and say that I have the H naught 3dTi as V over R H, and H is defined to be a matrix H plus H minus, and H plus minus is minus plus partial theta plus 1/2 cosine theta plus I partial phi divided by sine theta. Okay? So how would you actually obtain a solution to this problem? I'm sorry, there is a type. This is a cotangent. How would you obtain a solution to such a Hamiltonian? It's always the same thing that you do in the Dirac case. You square the Hamiltonian. Okay, so let's square the Hamiltonian. H squared is H plus H minus 0, 0, H minus H plus. And now you observe something I would say quite fascinating. You see in a second what I mean by that. So, who recognizes this differential operator? This is exactly the differential operator that we had for the Haldane sphere. So let me go. This is the upshot of the lecture. So when you go through this, okay, let me make another comment. You don't need to do all the hard work that you would do. Instead, you can just take this Hamiltonian and put in the gradient in spherical coordinates. Notice, however, that you need to take an Hermitian combination of the gradient in spherical coordinates, because the gradient by itself is not Hermitian. You can't just plug it in like this. You have to sort of Hermitianize the gradient operator. But if you do it, you can easily get this result that Murat got the hard way within 2 lines. It's 2 lines. Okay, but let me just, I only have 5 minutes left. Let me get this main message across that I wanted to tell you. You start with a 3D TI surface. You have a Dirac cone on the surface. Let's accept that for the moment. You get this Dirac operator either by smartly thinking about it or doing the hard work. And once you have that operator and you're trying to solve it, you square the Hamiltonian, which is something that you always do in the Dirac world. Okay? And as you square this operator, you get a 2x2 matrix that is diagonal. And on the diagonals, you get the direct, so you get the differential operator that you got on the Haldane sphere. Now, and maybe I should actually, so we will post the paper very soon, and then you can go through the calculations on your own. The main thing that I wanted to tell you is that using this differential operator now allows you to get single particle eigenstates in a very nice fashion on the surface of a 3D topological instrument. Of course, yeah, I'm sorry that I only have 2 hours. I would have needed 4 hours. But the main idea that I wanted to get across, I think, is still there. And let's be a bit more specific about what I mean by the Haldane sphere. What does the Haldane sphere have to do with such a 3D topological instrument? And here, that's the main thing. You see that the Dirac flux that we have, okay, so the Dirac flux is just one Dirac flux. It's one positive Dirac flux for the upper part of this 2x2 matrix and one negative Dirac flux for the lower part. Okay? So the system that we need to solve here is like a Haldane sphere, where for the upspins, I see a magnetic monopole of plus one Dirac quantum, and another problem of downspins seeing another Dirac flux quantum on opposite side. Okay? So, and where does this come from, this Dirac flux? This Dirac flux is nothing else but the very phase that a spin perceives as it rotates on the sphere. This is what it is. If you want to recast the very phase that you get by rotating a spin on a sphere as a magnetic monopole problem, you will find that the monopole that you need is just 2 pi. Okay? Just a Dirac monopole. So the 3DTI problem in your head can just be decomposed on the sphere as a positive sign magnetic monopole for upspins and a negative sign Dirac monopole for upspins and a negative sign Dirac monopole for downspins. I think that is quite remarkable. And whatever I said here can be just completely rigorous. You can just calculate everything you want here. Okay? So I think that is quite an amazing transfer from a Cornell sphere to a 3D topological insulator. And let me finish by saying how we then think of what is the challenge here. So the challenge in 3D topological insulators has never been to solve the single particle problem. Okay? So then last time I discussed the sphere for the quantum Hall problem, and people were asking me why do we even bother about the sphere. And my answer was that it was helpful for exact diagonalization to start treating the many-body problem in a way that has no boundary. Here, it is not completely unrelated. If you want to ask what happens to interacting 3D topological insulators, Sentil, who's unfortunately not here anymore, and many other people, leading scientists in the US mainly, have